Hello everyone, my name is Anton Kyrylenko, and as part of the CUNY Summer Undergraduate Research Program in the Photonics Initiative, I've worked on using the Drexage experiment for sound and applying it to acoustic metamaterials. My mentors were Dr. Diana Strickland and Dr. Andrea Alou. So what are acoustic metamaterials? They're specifically engineered materials that exhibit exotic interactions with sound waves. For this project, we were recreating an acoustic analog of the Drexage experiment that traditionally deals with light decay rates in front of an electric mirror. Images on the right display examples of acoustic metamaterials. The lower one showing non-reciprocity, where sound waves propagate through the material easily in one direction but get absorbed in the other. The upper image shows an example of an acoustic metamaterials structure that is tailored to the wavelengths that it interacts with. Many metamaterials are designed structurally to be at the same scale as the wave it interacts with. Thus, metamaterials that interact with light are designed at the nanoscale, whereas acoustic ones are at the visibly distinguishable scale. The model of the acoustic system was set up in the COMSOL simulation program, with a hardwall boundary made from concrete, a brass gong, and a sound source next to the gong, all inside an air-filled echoic chamber. In terms of the math, the amplitude of a wave, whether electromagnetic or acoustic, that is reflected by a mirror at any distance is represented by equation 1. Having an acoustic dipole in front of a hardwall mirror is based on a driven damped oscillator model, capturing the echo back action with equation 2. The solution to equation 2 yields the set of equations labeled 3, where gamma perpendicular and parallel denote the decay of the signal at different distances, with the dipole orientation being perpendicular or parallel to the mirror. And gamma infinity is the decay without a wall to be reflecting. Equation set 4 represent the frequency shift for the respective dipole orientations at varying distances. Working out the results of the previously mentioned equation set 3 in MATLAB yielded the following graphical representations. The leftmost image shows the perpendicular orientations of the electric dipole labeled A and the acoustic dipole labeled B. The left graph shows the comparison of the acoustic and light analogs of the experiment, where the y-axis shows the energies and the x-axis shows varying distances from the dipole. Note that these are time-independent results. The behavior of an acoustic perpendicular dipole is the same as an electric parallel one. While electric fields have a node at the conducting mirror's surface, pressure fields have an antinode, or the buildup of pressure at the hardwall mirror. Hence why the exactly opposite results of electric versus acoustic graphs. The varying radiation efficiencies graph on the right shows the changing coefficient eta only changes the amplitude. Radiation efficiency variation is due to the dissipation of energy into materials such as heat. Further results from MATLAB also yielded frequency shifts based on equation set 4 solutions. The graph shows the acoustic perpendicular examples shifts in the sound frequency based on distance, so not only amplitude changes as from the previous slide results, but also the frequency. Again, this is a snapshot of time. From the COMSOL model so far, I was able to set up the system to obtain the eigenfrequencies of the model and the visualization of the sound pressure levels in decibels. The left image shows a more bizarre response due to the varying boundary conditions, whereas the right image shows the higher pressure at the hard wall as expected, and the standing wave trough in between the gong and the wall. The spotted blue dots just mean that the mesh of the simulation wasn't fine enough due to the computational limitations, but it should just be a curve. The top right image shows the shape of the gong at its first resonating vibrational mode, which is the specific mode I needed. I have also started setting up a 3D version of the model in COMSOL, as it will be more intuitive visually. However, the 3D model will be used only if necessary, since it takes up much more computing power to solve. So far I have solved for the acoustic pressure field in the echoic chamber. However, it might need to be converted to an anechoic one to remove the echo from the back boundary. The concrete wall will then be replaced with a metamaterial to see the Drexage effects change. Newly developed and tested acoustic metamaterials can find themselves being applied to things such as sensing, which includes sonar and ultrasound, as well as materials that focus a sound propagation direction in different ways that haven't been done before. As for acknowledgements, I'd like to thank Dr. Alou and Dr. Strickland for accepting me into the program and the research group. It is one of the leading labs in metamaterials. I'd also like to thank the CSURP program as a whole for giving opportunities for undergraduates to expand their skills, knowledge, and networking in these kind of programs. And these are the references I used throughout the summer.